Okay, it's sometime in April, hopefully, and you're taking AP Chemistry, and you have a few remaining topics: organic, nuclear, and polymer chemistry. This is the final AP Chemistry lecture, and let's begin. Here's an email I received from an AP coordinator telling me exactly what you need to know for these topics, and this confirms the objectives and the experienced teacher that I work with, which is that there's very, very little to know if you're going to take AP Chemistry in terms of what's going to be tested on. You'll see that for organic chemistry, there's a few basic items that are good to know. Some honk rules, meaning hydrogen tends to form 1 bond, oxygen 2, nitrogen 3, and 4 for carbon. That's a little bit about organic chemistry. We study acids and bases deeply for AP Chemistry, and so this gets covered as it relates to organic substances. What is the pKa of something that's not an acid at all, like benzene, for example? Intermolecular forces get covered, and those are important for organic chemistry when you're considering boiling points and melting points and things like that. There we are. So that'll get interpreted. But that's about it for the SAT 2 test, which most students take in June, and a lot of the AP Chemistry students are going to take this test. There's all that material, and then there's like some of the core material for organic chemistry. Recognize that organic chemistry is a monstrous topic that gets taught in second year college chemistry typically, and there's a lot of people who make their career out of it. So there's a lot of material out there, but it gets covered in its basic format, meaning you cover some functional groups, things like aldehydes and ketones, how to name them. I mean, if I said a compound is called 2,3-butadiene, what would be its chemical structure? And does that even make sense? Polymers get covered a little bit in the SAT 2 test, but not in the AP test. And a few simple reactions. So for nuclear chemistry, look, there's nothing at all. For polymer chemistry, nada, which is good to know. So we are going to cover these materials a little bit. For those of you that want to take the SAT 2 test, this is a good idea. So we'll be talking about the basic types of nuclear reactions and a little bit about polymer chemistry. The reason we're doing it now is because it will help tie everything together and bring up those AP test scores. For example, you're going to see organic structures on the AP test, and it helps to be familiar with them. Half-life, we can extend our understanding of half-life. We've learned a little bit about it in the kinetics unit. And just as a general idea, it's good to understand how these things all fit together, and I think it leads to just a sort of organized mind. And so let's go ahead and begin. We're going to cover all these topics. This will be done by sort of a self-test format. So if you think you know the answer for any topic here, fill it in before I do to show me that you know it. Organic chemistry focuses on the chemistry of carbon compounds. If we draw the electron dot structures, the most common organic elements, we can get a feel for how they're going to behave. Hydrogen has its 1 valence electron. Oxygen has 6 valence electrons, but in accordance with Hund's rule, we're going to draw 2 lone pairs and 2 bonding electrons. Nitrogen has 5 valence electrons, so 1, 2, 3, 4. Whoop, somebody better be doubled up. 1 lone pair, 3 bonding electrons. Carbon, 4th column, 4 bonding electrons, no lone pairs. And therefore, if you see these things as the bonding electrons, you see that they often form 1, 2, 3, and 4 bonds respectively, giving you a lot of variety in terms of the substances that are formed. Compare that to salts, right? And things can get pretty complex, or can get pretty attuned to whatever desired need is required for those substances. So we can draw methane, by the way, honk, 1, 2, 3, and 4 bonds, typically, respectively. Things like ammonium salts can be violations of this rule, or extensions, if you will. So if we draw something like methane, carbon always forms 4 bonds. There they are. Hydrogen always forms 1. So we're good to go with hydrogen, we're good to go with carbon, and there is methane. Ethane has 2 carbons. If we surround this with the requisite number of hydrogens, 1, 2, 3, there's our 4 bonds on that carbon, 1, 2, 3, we get C2H6. And that looks good to go. Every carbon has 4 bonds, every hydrogen has 1 bond. Excellent. Propane, okay, let's do this. Form your backbone. When you start drawing these things, always draw the thing that forms the largest number of bonds in the center. Call that your backbone, and then extend out from there. That's a logical way to do this. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Let's draw them all for this structural formula. And that's C3H8. Let's see, 2n plus 2, 2n plus 2, 4 plus 2, 2n plus 2, 6 plus 2. We have a 2n plus 2 pattern for these saturated hydrocarbons. Saturated meaning no double bonds or rings or funny business going on. Now when we get to butane, C4H10, we could draw it the regular way. 1, 2, 3, 4. Now I'm going to get a little bit lazy. I hope this doesn't bother you too much, but I don't feel like drawing 10 hydrogens. So each line represents a hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. But you know what? I wonder if there's another way I could draw it. What if I branch it a little bit and do it this way? Now I'm feeling guilty, so I'm going to go ahead and draw every single hydrogen. 4 bonds on that carbon. 4 bonds on that one. That one, that one, that one. That one, that one, that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, this works. This is reasonable. This is called butane. This is called isobutane. And so these are called structural isomers. They're both C4H10. Now, have you noticed that it gets really annoying trying to draw all these things? Imagine drawing C10H22, something like that. So people came up with these skeletal structures, and check them out when I go ahead and draw them. I'm going to draw this one simply as, all right, that's it. I love this format. Zigzags. There's a carbon, there's a carbon, there's a carbon, there's a carbon. C4H10. 3 on that one, 2 on that one, 2 on that one, 3 on that one. This one, see if you could draw it. I'm coming up with like this little Mercedes benzene type of structure here, where it's just 3, 6, 9. Where's my 10th? Right there, since there's only 3 bonds. So that's one beautiful view of how things can branch and lots of isomers can become possible. Another form of complexity is that there's no reason these can't cycle around and form a ring. And so if we draw C3H4, we can do this. Oh, carbon, carbon, carbon. But if I start drawing my double bonds, if I start drawing my bonds, 3, 4, 5, 6, 7, 8, I want to draw only 4. How am I going to do that? I need to like bring in some serious bonding type thing. How about that? Even if I do that, it's going to be C3H6, so I'm going to get rid of that one. And I'm going to go ahead and do 2 bonds there. And that looks like a pentavalent carbon there. So I can go like that. I can go like that. I can go like that. H, 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 H. Well, that's one way to do it. So we can also get creative. I could do this. That's it. That's a carbon. That's a carbon. That's a carbon. It's called propane. C3H4. 3 on that one, none on that one, and 1 on that one. And check out this structure. Here's getting really creative. Stop that. 1, 2, 3, 4. Will that be C3H4? 1, 2, 3, 4, 5. Oops, that's not even C3. C3H246. I better put in a double bond. That's C3H4. 3 isomers? Well, let's just draw one more. How about C3? That's 1. That's 2. We need another one. How about something like 1, 1, 2. You know, I don't know if we're going to come up with another isomer here because that won't work. If I stick it together, that's that one. Is it possible that there's only 2 isomers of C3H4? Ah, wait a minute. How about this? How about that? 1, 2, 3, 4. Notice how this carbon has already got all its 4 bonds, so that's another one. Sometimes they can show the stereochemistry by wedges and hatches. So if we have a substance like this, which by the way is called cyclopropane, and we put a chlorine on it right there, and we draw a big fat wedge like that, that's in stark contrast to a chlorine right there. And what this is meant to imply, it's really almost like this. This is coming out of the plane of the board or of this laptop towards you. Get that? That's the way you draw it as a wedge. This one is disappearing into the plane of the board, and they're in a far away position, right? If I drew it like this, whoop, that's a wedge. Now they're in a closer position. They're both coming up. And so that's a little bit about stereochemistry. There's many other examples you can come up with. For example, let's skip it. Okay, let's review. What's organic chemistry? The study of carbon compounds. What are structural isomers? Well, they had the same molecular formula, but they had a different fixed shape. I say fixed because I hope you're starting to realize that if I just take the hydrogens on something like butane, like this, they're free to rotate around. And so if I try to show them as being, I don't know, different angles, that's not an isomer. Things have to be a different fixed shape, and that comes with a little bit of practice. How many bonds does nitrogen typically form? 1, 2, 3, 4. It must be 3. So that's more organic substances. They comprise several common functional groups. Here they are, most of the common functional groups. I think we'll add one right here. That's supposed to be linear, but I want to emphasize that there's a carbon there. And so what are they? Can I click on this to make it reveal? I don't think I can. So we'll just, maybe if I go like this. Nope. Okay, these are called alkanes. No double bonds. Double bonds means alkenes. Have you heard these before? Alkynes with triple bonds. Ethers have an oxygen with carbons on either side, no double bonds. If that oxygen is at the end of the chain, since oxygen forms 1, 2 bonds, these are called alcohols, almost like terminal ethers, if you will. These substances with nitrogens in them are amines. It won't show up in the slide, but that's a terminal amine. It'll have 2 hydrogens. We also call that a primary amine. This one with carbons on either side and would have 1H is a secondary amine. And if you had one that was with 3 substituents on it, that would be a tertiary amine. This group here is not a functional group. It's kind of just a part of a functional group called a carbonyl group. And they show up here, they show up here, they show up here, here, here. They all have carbonyls in them. If that's it and it's at the end, meaning we have a hydrogen attached there, those are called aldehydes. If it's in the middle with an oxygen attached to it, well, they smell nice. Those are called esters. Not sure why I skipped these, but you got a carbonyl group just in the middle, but no oxygen on the other side. We call those ketones. Nature is full of all these substances, especially these. These are the building blocks of amino acids, which go on to make proteins in your body. Building blocks of life. And these are called amides. Notice it's like an ester, only with a nitrogen instead of an oxygen. And if it's a terminal ester, if you will, a carbonyl with an oxygen next to it, but no carbon on this side, just a hydrogen, that's one of the rare acidic organic substances. This is called a carboxylic acid. Okay. Don't seem to be capable of showing another slide. By the way, this is a nitrile, also called cyanides, but organic cyanides. They oftentimes can be toxic substances. And that's a C triple bond N group. I think we'll stop here since I can't seem to get to another slide. And this is a little bit about organic chemistry for AP and the SAT 2 subject test.